Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the problems which are based on viscosity. So in this first question, you can see that during a coating process, a thin flat tape of width W is the width which is measured inside this plane. Okay, and the length L. In fact, this tape is passed or dragged through a channel whose length is L, and this channel is containing a Newtonian fluid of density rho. This fluid is the paint which is to be coated on this tape, and the dynamic viscosity of the fluid is mu, which is viscosity coefficient. This fluid is in contact with both sides of the tape, and we have to apply some force to pull this tape outside this channel with a constant velocity v. The the gap of the channel is h, and we have to assume that this thickness of the tape is negligible as compared to h. So we have to find out this force required to pull this tape so that it moves with a constant velocity. So we can see obviously that this liquid will be applying viscous force on both of the sides of the tape, and the viscous force on any one side of the tape will be mu, which is neta a into dv by dz, and F will be equal to mu, and area will be L into depth is W. Okay, so L into W, and the velocity of the tape is V, and dz is the gap between these this surface of the tape. Let me show you like this. So this surface of the tape and this surface of the channel, this is dz, and this is obviously h by 2. So this is dz is h by 2. So F is equal to 2 mu L W V by h. And obviously we know that to keep this tape moving with a constant speed, we need to apply a force which is exactly equal to this complete total viscous force. So F will be equal to twice of F. So F will be equal to 4 mu L W V by h. This is the value of F. So the correct answer is A. Now we move on the next question. In this question, you can see that there is a thin plate which separates two liquids of coefficients neta and 4 neta. So this is a thin plate which is separating these two liquids of coefficient neta and 4 neta. And this thin plate is kept fixed between these two plates. Okay. And this thin plate is needed to be pulled outside this arrangement with a minimum force. So we have to find out the value of d2 upon d1. So we can easily predict that the viscous force applied by the upper liquid will be F1, and the viscous force applied by the lower liquid will be F2. And if we write down the viscous force of the upper liquid, then we can say that F1, viscous force of the upper liquid, will be F1, and it would be equal to neta into area is, let's suppose, A, and velocity is, let's suppose, V. Okay, and the width of this upper layer of the liquid is d. So this is neta A dv by dz, and similarly F2 will be equal to 4 neta A into velocity is v, and this is d2. Okay, and we can say that the applied force F will be equal to sum of these two forces to keep this plate moving with the constant velocity. So we can say that it is neta A into V by d1 plus this is 4 neta A into V by d2. So let us take common, this is neta A V, and this is 1 by d1 plus 4 by d2. Now we have to find out the minimum value of force. So we can obviously know that if this is D, then we can say that dF will be equal to neta AV, and let us differentiate these two terms. So after differentiating these two terms, we can say that it is equal to minus d1 by d1 square plus 4 d2 by d2 square, and let us equate it to 0, and this will be minus obviously. So we can say that d1 by d1 square is equal to minus of 4 d2 by d2 square. This is the first equation. And if we find out the value of d1 upon d2, so this will be d1 upon d2 will be equal to minus of 4 d1 square by d2 square. And we also know that d1 plus d2 is equal to d. So differentiating these terms, d1 plus d2 is equal to 0. Okay, so we can say that d1 is equal to minus of d2. So d1 upon d2 is 1, minus 1. So this is minus 1 and this is minus 4 d1 square by d2 square. So d1 by d2 will be equal to 1 by 2. So we have to find out the value of d2 by d1. So d2 by d1 will be equal to 2. So the correct answer will be option B. Now we move on the next question. In this question, you can see that there is a section of pipe of length L, and the radius of pipe is R, and a liquid is flowing through this cylindrical pipe, and the pressure at the two ends of the pipe is constant, and therefore the pressure difference is also constant. So it is given that the velocity of liquid flowing through the pipe has a velocity v naught at the axis of the pipe, and the coefficient of viscosity of the liquid is neta. So we have to find out the velocity of the liquid at a distance of r naught by 2, root 2 from the axis. We already know that in this type of laminar flow, the liquid layers are in the form of cylinders, coaxial cylinders, and they have different velocities at different distance from the central axis. And this formula of velocity we have already discussed in Poiseuille's equation. I'll show you. This was the topic, volume rate flow through the pipe, Poiseuille's equation. And in this topic we have already discussed this formula, where V naught is the velocity of the liquid at the axis of the cylinder. Okay, so this V is V naught 1 minus R square by R square. So we will use this formula directly here, and therefore we can say that V is equal to V naught into 1 minus R square by R square, and V is V naught, and this is 1 minus, this is R naught square by 2, and this is R naught square. So this will be equal to V naught by 2. So the value of N in this term will be 2. So the correct answer is 2. Now we move on the next question. In this question you can see that there is a circular disc of diameter D. So let us identify the disk. So this is a disk and this is the axis of the disk, and this disk is rotating about this axis with an angular velocity of omega, and this is the radius of disk, which is d by 2, and we have to rotate this disk with a constant angular velocity omega on a liquid layer of thickness h and viscosity coefficient mu. So we know that due to the viscous force applied by the liquid on the disk will retard, and there will be a retarding torque which will be produced by the viscous force on the disk. So if we apply some equal and opposite torque on the disk, then disk will keep on rotating with the constant angular velocity. So we have to find out that torque which we need to apply on the disk so that it keeps on rotating with a constant angular velocity. So obviously the torque applied by us should be numerically equal to the torque applied by the viscous liquid on the disk. So we just need to find out the torque applied by the viscous liquid on the disk. So let us first of all draw the cross-sectional view of the disk. This is disk, and there is a liquid layer on the disk, obviously, and that liquid, now we also know that if the velocity of the angular velocity of the disk is omega, then at each point at a different distance from the center of the disk, let us draw that point. So let us suppose that at this point, which is at a distance of r from the disk, the velocity of this point will be different, and at a distance of 2r it would be different because v will be equal to r omega. So we have to assume an element, and because due to the different velocity, the viscous force acting on this different elements will be different. And let us suppose that the width of this element is dr and the radius of this element is r. So we can say that the velocity of this element v will be equal to r omega. This is v is equal to r omega. Okay. And the viscous force will be acting just in the reverse direction, df. Like that. Okay, and this is df. So we can write down the value of df, that df is equal to mu into area. Area will be 2 pi r dr into dv by dz. Now v will be r omega and dz will be the thickness of this liquid layer, which is h. So df will be equal to 2 pi mu omega by h into r square dr, and d tau torque will be df into r. So d tau will be equal to 2 pi mu omega by h into r cube dr, and total torque will be 2 pi mu omega by h, and this is r to the power 4 by 4. I have already integrated this term, and the value of r is d by 2. So torque will be equal to pi mu omega r to the power 4 divided by 32h. If we compare it with this term, which is pi mu omega d to the power 4, this will be d, obviously. We have substituted the value of d. So we have substituted the value of r. So this is x h into 8. So the value of x will be equal to 4. Okay, so this is the correct answer. Now we move on to the next question. In this question, you can see that there is a sphere, a spherical ball. Let us draw the scenario that this is a separation which separate, this is an interface which separate a liquid of density sigma with a vacuum or air, and this is a sphere of density rho. It is dropped from some height h and rho is greater than sigma. So we have to choose the incorrect option. The acceleration of the sphere just after entering the liquid will be. Now see, if the sphere enters the liquid with, obviously sphere will hit the liquid with some velocity u. So this force will be mg, this will be buoyancy, and there will be viscous force also acting on the sphere. So the acceleration of the sphere will be actually A will be equal to mg minus buoyancy minus viscous force upon m. But this option says that A will be only mg minus buoyancy upon m. So A is incorrect. So we have to choose the incorrect option only. So A will be the correct choice. And the time taken by the sphere to attain the terminal speed does not depend on rho. Obviously, we know that the time taken by the sphere to attain the terminal speed is infinity. So it does not depend on rho in any case. So obviously B will be the correct answer, but B will be the correct, B is a correct option, but B is not the answer because we have to pick the incorrect one. So B is not correct. Now at terminal speed, viscous force will be maximum. So obviously viscous force depends on the speed of the sphere, which is 6 pi neta rv, and terminal speed is the maximum speed. So at terminal speed viscous force will be maximum. So this option is also factually correct, but this is not the answer. At terminal speed the net force acting on the sphere will be 0. This is also factually correct because at terminal speed net force acting on the sphere is 0, and therefore this is also not the correct answer. So correct answer is only option A. Now we move on the next question. In this question you can see that the velocity distribution in a viscous flow over a plate is given by u is equal to 4y minus y square. So actually this is the velocity of liquid at a height of y from a stationary plate, and we have to find out the shear stress at y is equal to 0. So we know that the viscous force will be neta A into dv by dz, and in this case the shear stress will be equal to F by A, and it would be neta into dv by dy. So neta is 1.5, which is 3 by 2, and dv by dy, u is equal to 4y minus y square. So du by dy is 4. Okay, 4 minus 2y, and at y is equal to 0, du by dy is 4. So this is 4. So the shear stress will be 6 Newton per meter square. So the correct answer is 6. Now we move on the next question. In this question, you can see that there are two balls of radii r and r by 2 which are released inside a deep water tank, and their initial accelerations are found to be g by 2 and g by 4. So the initial acceleration of this ball is g by 2 and of this ball is g by 4. We have to find out the relative velocity of the smaller ball with respect to the larger ball long time after these balls are released, and the coefficient of viscosity is given as neta. And in this question it is given that the liquid is water, so we can assume that sigma is 1, and we do not know rho. So the value of rho is unknown. Rho is the density of the balls, and we can assume that density of each ball is same. So for the first ball we can say that the mg minus buoyancy for the first ball is m a, and a is g by 4, and we can also assume the mass of the first ball as m1. And obviously the mass of the ball can be written as volume V into density rho into G minus buoyancy is V into sigma, and sigma is 1 into G, and this is V into rho into G by 4, cancelling V and G in the terms. So rho minus this is G by 2. In fact, for the first ball it is G by 2. So rho minus 1 is equal to rho by 2. So rho is equal to 2, first of all. And we know that for the second ball, M2G minus buoyancy will be equal to M2A. A is G by 4. And obviously, when these balls will attain the terminal velocity, the net force acting on the balls will become 0. And mg minus buoyancy will be balanced out by viscous force. So we can say that for the first ball, m1g minus buoyancy will be equal to F viscous, which is 6 pi neta r v1, and it would be equal to m1g by 2. So it is 6 pi neta r v1. And for the second ball, m2g by 4 will be equal to 6 pi neta r v2. Let us write these equations on the next page. So we can say that for the first ball, this m1g by 2 is equal to 6 pi neta r v1, 6 pi neta r v1. And for the second ball, m2g by 4 is equal to 6 pi neta r v2, 6 pi neta r v2. This we can easily say. Now we know that the mass of the first ball, m1, will be the density rho, which is obviously we can use the value of density as 2. So let us first of all write down in the terms of rho. So rho into 4 by 3 pi r cube into G by 2, and that is equal to 6 pi neta r v1. So cancelling pi with pi, this 2 with 2, this 2 with this 2. So v1 will be equal to rho r square G by 9 neta. And rho is 2, so v1 is equal to 2 r square G by 9 neta. And similarly, for second ball, mass density is rho, volume is 4 by 3 pi r cube by 8, because radius is 1 by 8. This is G divided by 4 is equal to 6 pi neta, and this is r by 2 into v2. And obviously cancelling pi with pi, and this 4 with 4, and this 2 with this 3. So rho is 2. So rho g r square, rho g r square by 24 into 3. Okay, and neta. This is v2. Now rho is 2. So g r square by, this is 12 into 3, 36 neta. This is v2. Okay, and rho is 2 obviously. So v2 minus v1 will be equal to g r square by 9 neta and 1 by 4 minus 2 by 1. So this will be minus 7 by 36, minus 7 by 36 g r square by neta. We have to find the relative velocity of smaller ball with respect to the bigger ball. So this will be the correct answer. Now we move on to the next question. In this question, you can see that there is a hollow cylindrical pipe which is filled with a Newtonian fluid, and there is another coaxial cylinder which is of radius small r, capital R, and the radius of the pipe is 2r. Now the velocity of this cylinder, hollow cylindrical pipe, is 2v0 in the backward direction, and the velocity of this inner cylinder is V0 in the front direction. The pipe is moving with a constant velocity of 2 V0, while this inner cylinder is moving with the constant velocity of V0. And to keep this cylinder moving with the constant velocity, a force is needed to be applied on the cylinder. So we have to find out this force, that how much will be this force. So I have already drawn this diagram here. You can imagine a cylinder like this, and this cylinder is experiencing some viscous force acting on it in the backward direction. This viscous force will be 6, in fact this will be neta into area is 2 pi r. The radius of this cylinder is small r, into L is its length, into dv by dr, where dv by dr is the velocity gradient with the radius. Now as we know that this velocity is also constant, all the velocities are constant. Therefore, the net force on all the cylinders will be 0. So this force will be equal to the force which we have applied, F0. Okay, and the velocity gradient will be negative because as we are moving away from the axis of the common axis of the cylinders, the velocity is decreasing. So we can say that 2 pi neta L by F0 into dv with a negative sign is equal to dr by r, integrating both the sides. And the radius, limit of the radius will be from capital R to 2r, and the limit of velocity will be from v0 to minus 2 v0, because the direction of these velocities is in opposite direction. So this is 2 pi neta L by F0, and this is 3 v0, and that is equal to ln2. So F0 by L, the force per unit length, is equal to 6 pi neta v0 by ln2. So the correct answer will be option B. And now we have to find out the distance from the axis, common axis, where the velocity of the fluid will be 0. So to find out the distance, we integrate this term again, and we can see that minus 2 pi neta into L by F0, and the integration of dv, and the integration of dv will be from v0 to 0, and it will be equal to ln2. In fact ln r by r, because now the limit will be from capital R to small r. Okay, and this will be 2 pi neta L by F0 and V0 is equal to ln R by R. Now the value of F0 will be F0 by L will be 6 pi neta V0 by ln2. So we can substitute F0 by L. This is 2 pi neta V0 divided by 6 pi neta V0 by ln2 is equal to ln R by R. Okay, and cancelling this with this, V0 with V0, this is ln2 to the power 1 by 3 is equal to ln R by R. So R is equal to capital R into 2 to the power 1 by 3. So the distance from the axis where the velocity will become 0 will be 2 to the power 1 by 3 into R. So that's it in this video. I'll be bringing some more concepts on surface tension in the next video. Thank you.